Baby shotties, how we doing today? All right, so in the second section, we're going to look now a little bit more deeper into types of energy. So mainly what we talked about last section was the idea of work, and work is applying a force over a certain distance that's going to add or remove energy into an object. So when we add or remove energy, we can add or remove energy into different types. So what we're going to do is we're going to specifically look at what's called mechanical energy. So mechanical energy is looking at specific forms. So there are many different types of energies that I talked about in the previous lesson, like chemical energy, electrical energy, and so on and so on. When we look at mechanical energy, we're looking at just more of the physical side of it. So there's really going to be two types, again, of energy in general. There's what's called potential energy, which is going to be energy stored that can be used for later, and there's what's called kinetic energy. So we're going to look at more so just the physical objects having potential energy, objects having kinetic energy. In terms of potential energy, we're going to look at two of them. We're going to look at what's called gravitational potential energy and inelastic potential energy. And then kinetic, we're just going to look at just kinetic energy as a basic form of objects moving. All right, so in terms of the types of energy, the first one we have is what's called gravitational potential energy. So again, anytime we use the word potential, we're thinking about energy being stored. So in this case, it's going to be stored due to the height of an object off the ground. So the idea of potential, again, is it's stored relative to something. And normally when we use the word potential, it's going to be stored relative to some sort of position. So again, this is going to be stored relative to the height off the ground. So you'll see in this, just a little diagram here. I don't know if you can't draw this, this is just like a pendulum, but what this is trying to show you is that the higher up this guy is, so notice here's where he's got his maximum height, is where he's going to have the most potential energy. As he goes down, his height is really low here, so he's going to have little potential energy, and then somewhere in between, you know, not too hot, not too cold, kind of like porridge, he's going to have some sort of potential energy kind of in the middle. So potential energy is going to be based upon the height. You'll see here that potential energy we're symbolizing with a PE, just in general, PE, potential energy. When we talk about gravitational potential energy, the way that I'm going to symbolize this is EG. Very similar to when we use forces, I wrote FG, but E is going to stand for energy. You might also see me write, sometimes I might just write this as PE, or I might write GPE for gravitational potential energy. Equation-wise, make sure you write this down. There is a way that we can actually figure out quantitatively how much energy we have, and it's mgh. So m represents the mass of an object. Let me just jot this down. M represents the mass, and again, mass is measured in kilograms. G is that value of gravity, and h is the height of the object. So it's based upon the mass, which again is how much stuff it's made of, so the bigger object's going to have more energy, and also based upon the height. So let's just say that I have a 50 kilogram box lifted to a height of 1.5 meters. How much gravitational potential energy would it have? So gravitational potential energy would be the mass times gravity times the height. So it would be 50 kilograms times a gravity, which is 10, times a height of 1.5. which will give me a total of 750 joules of gravitational potential energy. That's how much energy, again, it's going to have based upon its mass and its height. Second type of potential energy we're going to look at is what's called elastic potential energy. So elastic potential, again, the word potential is being used because it's stored. Elastic is going to be stored due to objects that can stretch, compress. So you can think of maybe like a cord that can stretch, like a bungee cord, maybe a ball that can bounce, a spring. Anything that can stretch and that can return back to its original position is going to have that elastic potential energy. So again, elastic potential energy, again, it could just symbolize it as PE and just knowing that it's elastic, but you'll see here that I use EL. EL stands for elastic, the capital E stands for energy. The equation that you're given is 1/2 K times delta L squared. So real quick, what the heck are these variables? So K is what's called the elastic constant. Sometimes it'll be referred to as the spring constant, depending on what the type of elastic object we're using. But it's just that elastic constant, is going to be labeled as newtons per meter, and it's going to describe how stretchy that object is, okay, or how much force is required to stretch it. Delta L is going to be its change in length. Okay, so when we talk about, like, let's say this bow and arrow here being stretched, that cable has some length to it, and when the guy pulls back, you'll notice it stretches. So what happens is that its length is changing. He's making that string longer, which is going to add elastic potential energy into it. And notice that that change in length is squared, because the more length you give it, the more energy is going to be stored. And those that might have used a bow and arrow before know that as you pull this thing back, the difficulty of it to pull back, the longer it gets, is going to increase, which means it's just having more energy. So it's called elastic potential energy. So let's just say that I had a spring. Okay, this is using a bow and arrow, but let's say I have a spring who has a spring constant. So think of that elastic constant, a spring constant of 200 newtons per meter. So when you see that newtons per meter, just know that that is that K value, that elastic constant, and it changes its length by 0.2 meters. How much energy would it have? So if I'm stretching something, again, it's elastic potential energy, so it's simply half of K times that change in length squared. So K is going to be 200, so it's half of 200 times the change in length, which is 0.20. Squaring that is going to give me then a total of 4 joules of elastic potential energy. So again, it's based upon that elastic constant and that change in length. All right, the last form of mechanical energy we're going to look at is what's called kinetic energy. So know that kinetic energy is completely different than potential energy. Kinetic energy is energy being used. And this is based off of potential energy, but if I give something stored energy, obviously it wants to use it. We eat food so that we have energy to do things, right? So kinetic energy is going to be the energy used, but more so it's going to be used in terms of motion. So it's going to be, think about it as the energy associated with how much motion it has. Very similar to that concept of momentum that we talked about last chapter. Energy is very similar to momentum. It's going to describe how much oomph that object has as it's moving. All right, so to symbolize kinetic energy, you're going to see it two ways. You might see KE being used, or you'll see me use EK kind of in reverse, but again, energy, K represents kinetic. It's based upon two things. Based upon the mass of the object, so how much mass it has measured in kilograms, and then V represents the speed or velocity, how fast it's going, measured in meters per second. So notice it's measuring mass and speed, very similar to momentum, but the equation is a little bit different because energy and momentum are related but not the same thing, but it's 1/2 mv squared. So for example, if I have a mass of 1,500 kilograms of a car moving with a speed of 25 meters per second, momentum-wise, all I would do is multiply those two things to get momentum. But in terms of the kinetic energy, I'm going to take half of its mass times the speed squared, so it'd be half of 1,500 times 25 squared, and that's going to tell me how much kinetic energy I have. Big dog number here, I'm going to get 468,750 joules. No rounding there, that's exactly what you would get. But again, that's a lot of energy because you have a car moving at about 25 meters per second, which is close to 50 miles per hour, so that's a lot of energy that it has. So we have the three types. We have elastic potential energy, gravitational potential energy, and kinetic energy. So kind of connect this. This is one of the main ideas. So there's really two main ideas that we're going to look at this chapter, and they're going to be in this one little section. First thing, we talked about work in our last video. On work was the ability to add or remove energy to something. Obviously, that when you do work, you're giving something energy. So this is what's called the work energy theorem, is that the amount of work done by an object is going to equal a change in mechanical energy. So think about work as a process again. Work was a force times a distance times that cosine of the angle. Again, that was just the angle between them. What that is going to do is it's going to change the amount of energy a system could have. Now, in terms of changing the energy, two things could happen. You could gain or lose kinetic energy, so there could be a change in kinetic, or there could be a change in the potential energy of that system. But when you do work onto an object, it's going to add or remove energy in different forms. So for example, if you swing a hammer, okay, when you swing a hammer, you're applying a force to that hammer, you're making that hammer move. So when you swing the hammer, you're giving it kinetic energy. That kinetic energy can then be applied to a nail. You apply a force over a distance, it's going to drive the nail into the wood. It's going to make that nail move into the wood. So again, work equaling kinetic energy. You can look at this down here. This is a wrecking ball, okay? Frickin' Miley Cyrus, you know what I'm talking about? But we lift up that wrecking ball. We're giving it potential energy, but we're doing work to lift this thing up, giving it stored energy. It's then going to swing down. That stored energy is going to turn into kinetic, and then that kinetic energy is going to slam into the object, and that kinetic energy, again, is going to be applying work to that building, and that work is going to cause that building to crush. Okay, but when we do work, we are adding or removing energy into a system in one of the forms. It could be in gravitational, elastic, or kinetic, and that's what we're going to look at next. All right, so let's say that I take a loaded cart. So it says here, a cart is loaded with a brick and pulled with a 15 Newton force at a constant speed along a 0.9 meter ramp. So on just diagram real quick, we know that this force is 15 newtons. I know that the distance here that it travels is going to be 0.9 meters. It says that the mass of the loaded cart is 3 kilograms and is pulled to a height of 0.45 meters. So let's just say in the end that the height that it reaches is 0.45 meters. So if I want to find the amount of work done, the work is going to be equal to the force times the distance times the cosine of the angle between them. Ignoring the ramp, notice that the force is being applied in the direction of the ramp or up the ramp, the distance it moves it up the ramp. So simply to find the work done, I'm going to take 15 newtons times 0.9 meters, and again, the angle between those two things is going to be 0 degrees. So in terms of the amount of work done, I'm going to get a total of 13.5 joules of work being done. Okay, now, this is the idea we're going to connect. When we do work, what type of energy does this cart gain? So obviously, as I'm lifting it up the ramp, the key thing is that I'm going to lift it from being at the bottom of the ramp up to a new height. So what am I changing is by lifting this thing up the ramp, I am changing its height. So by changing its height, that means the amount of energy it gains would be potential energy, and specifically, it's going to be that gravitational potential energy, EG. So if we looked at it, okay, the cart is, let's say, at that height measured there, how much energy would it have? Well, the gravitational potential energy can be determined by taking the mass times gravity times the height. So if I take the mass of this cart, which is 3 kilograms, I multiply it by gravity, which is 10, and I know it's being pulled to a height of 0.45 meters. If I multiply these three things together, what I'm going to get is 13.5 joules. And what I want to show here is that the amount of work that's being done, and initially just to lift this thing up, that amount of work, that amount of energy goes somewhere. In this case, that energy goes towards gravitational potential energy. It now has energy that it didn't have before from applying that force. So the idea here, if I'm going to write this all together, is that when I apply a force over a distance, consider the angle in between them, it's going to cause that object to gain height. And now that's a lot of stuff going on there, but that's kind of what's going on in this one equation. The key thing here is that they're equal. The amount of work done equals the amount of energy gained. You can apply the same idea to that bow and arrow type system we looked at. So let's say that it takes a 750 Newton force being applied to that bow and arrow system to stretch it back 0.4 meters. So obviously when you do that, work is being done. You are applying a force backwards. That object is going to move backwards. So if I want to find the work, it's going to be equal to the force times the distance times the angle in between them. So it'd be 750 newtons times 0.4 meters. And again, the angle in this case, very simple, is going to be 0 degrees. So in total, you'd get 300 joules of work being done by stretching that thing back. Now, obviously, if it's a bow and arrow system, what sort of energy does it gain? In this case, it's going to gain potential energy again, energy stored. In this case, it's going to be called elastic potential energy, energy stored because that is an elastic system. It's going to stretch. So if I want to know how much elastic potential energy it gains, I can use that relationship. 1/2 K times delta L squared, where K is that elastic constant and L is its change in length. So if I want to use my values I'm given, I know the elastic constant is 3750. Okay, that's a big number because obviously it takes a little bit of oomph to pull that bow and arrow back. And then I know it's being stretched, again, a distance of 0.4 meters, as it says in the problem. So just using that formula, what I get then is, you guessed it, hopefully, 300 joules. Because, just like the previous problem, the amount of work that you do should give energy to a certain form. So in this case, it's going to give energy in the form of elastic potential energy. So those values should be the same. So this is what's called the work and energy theorem, that work is going to add or remove energy from an object. All right, now to make the connection between those types of energy and kinetic energy. So if we look back to that cart in number 1, it was at the top of the incline, and let's say that we were to release that object. I'll just kind of draw a sketch, but it was on a ramp. It was at a new height, if you remember, of 0.45 meters. Oopsies, that's just 0.4 meters. But obviously, if I let this thing go as it goes down the ramp, I know it's a cart, but I'm going to draw as a ball, that obviously it should gain speed. So I want to know how fast would it be going at the ball. Now, this is actually something we could have done a long time ago using, say, Newton's laws or using the kinematic equations, things that we learned back in our early chapters. But what I can do is this now, is I know that at the top here it's got gravitational potential energy. And we said, based on that first example, that it had 13.5 joules of potential energy. So therefore, at the bottom, if it has kinetic energy, what's happening here is that obviously this energy is being stored, but any energy that's being stored is going to be used. So as it goes down, it's obviously going to take that stored energy, and as it loses height, it's going to gain speed, and we're going to see that it's going to gain all that energy in terms of kinetic energy. So that same 13.5 joules that was initially, sorry, not newtons, but joules, that was initially given to you as work in the form of gravitational potential energy is going to turn into kinetic. So knowing that my kinetic energy is equal to 1/2 mv squared, I can solve for v using this simple relationship. I know the energy is 13.5 joules. Based on problem number 1, the cart had a mass of 3 kilograms, so therefore what would its speed be? So showing the algebra here, you should get a speed of about 3 meters per second. But again, the idea, we did work to bring the cart up to this height, giving it gravitational potential energy, but then it needs to be used, and energy that is used always goes in the form of kinetic energy in terms of physical object. So therefore, we said it's the same amount of energy used as kinetic, which then allows us to find speed. So using these ideas of energy actually simplifies some of the problems that made it a little bit more complicated. Okay, one more example for this, just this part of the lesson. Let's take that same idea but now apply it to the bow and arrow system. So let's say I want to find the kinetic energy and the speed at which the bow or the arrow leaves the bow. So again, in that case, we knew that when we stretched back the bow, it had elastic potential energy, and we said that it had 300 joules of elastic potential energy. Okay, so the idea here is that when you launch that arrow is going to move with some speed, so it's going to have kinetic energy. Oopsie daisies. So in this case, if it had 300 joules of stored energy, that 300 joules is going to go into kinetic energy. So if I know that kinetic energy is equal to 1/2 mv squared, I can solve for the speed by saying, okay, that's 300 joules of energy. I know that the mass of that arrow that's given to me in this problem is 0.02, then I can find the speed. And then you can follow the algebra, and you'd get a speed of about 173 meters per second. So again, that's flying, but that bow and arrow being very light is going to move very fast. But again, this is looking at the idea of work and the different forms of energy. Know that work is a process of adding or removing energy, and then we can use those energy relationships to actually solve for speed, solve for height, whatever it might be. You guys got any questions on this, write down. I know there's a couple more examples, but you'll check out the second video lesson for this section on the law of conservation momentum. See you guys later. Peace out.